Hi, my name's Adam Timlett. I'm the founder of a consultancy which is interested in helping companies with organizational analytics. So I think that organizational analytics is something that we don't maybe pay that much attention to. We focus more on, you know, the kind of like classic kind of KPIs and things that we have a lot of data, you know, to work with. And I think that organizational analytics is something that's not sort of dealt with. Like if you go onto the job market and you look at kind of like data jobs, you won't see that much, you know, going on in terms of people analytics relative to other types of analytics. So so this talk is about organizational analytics, and I'll talk about why I don't think there is that much going on with people analytics. And apologies to people who are working with organizational analytics and stuff. If they are there, I'd be really interested to talk to you and talk to about it. But I'll explain in the talk what my consultancy is about. So I'm the founder of Turing Meta, which is this company that looks at organizational analytics. And this talk is about how to see your organization's dragon. So what do I mean by that? So this is a physicist called John Wheeler, and he said a long time ago, he talked about the great smoky dragon of quantum mechanics. And what he was referring to was something that was very hard to measure, and something that was too big in some sense to measure. And so it was a kind of at the limits of our knowledge of science. And so he obviously used the analogy of a dragon as something that's big, but because it's so big, you can't actually measure it. And so he thinks of a dragon as something that's big, but hard to see. And I think that's what organizations are. They're too big for us to measure them, right? Because obviously if you have a small organization, say 10 people, you know exactly what everyone is doing. That's perfectly possible. But once you get to, say, 150 people, right, nobody knows the whole organization. Is too big, right? If you were just to spend time with each team in that organization, doing complex work and getting to know each team, say 3 people, for a year, you get a solid understanding of what they do. But in an organization of, say, 200 people, that would take you 76 years just to be 1 year in each team. And if someone's in a team for a year, do you think of them as experienced? We think of them as beginners in most jobs. So this is what I mean by the dragon. And my consultancy is about how do you measure this that you can't experience. And so the problem actually gets worse, because not only can we not experience directly, you know, medium-sized organizations. I mean, these are small, really. 150 people is small compared to lots of organizations, but we can't experience it directly, and we can't measure it directly. And that sounds funny, because obviously we're in an analytics meetup, and so we deal with measuring things all the time. I'm an analytics manager in my other job. But the reason I say that we can't actually measure organizations either is because it's not easy to measure things scientifically, which means that what I mean by that is, to measure something scientifically, you need to do controlled experiments. And controlled experiments are not easy to do. They're expensive, actually, and they're difficult. They involve, like in pharmacology and medical science, you need to run what's called a double-blind trial to avoid fooling yourself that you've seen something that you haven't really seen. And a double-blind trial can't be done in an economics context, because people know what pill, if you like, you're getting. You can't disguise and say that's a placebo. You didn't get the real economic intervention. It's not possible. So this is what I mean when I say we can't measure them. So organizations are big, yet they're also hard to see. And if we look at the bar as controlled experiments in terms of scientific knowledge, measuring something with certainty that we know what it's telling us, then management science is way below the bar, because it tries to directly measure things which you can't do controlled experiments on. If you look at organizational economics, it's not very different. It's the same scenario. And if you look at economics in general, obviously macroeconomics, it's even, if it's possible, it's even worse. You know, we're not dealing with a scientific process here. We're dealing with people's subjective judgments filtered through data that is entirely subjective, because it doesn't allow you to filter out through direct contact with reality. And science relies on people having contact with reality, which only comes from controlled experiments. So if I look at the sciences that are real, I would say, then physics is the gold standard, because you can control the things that you're measuring. Now, obviously, after 300 years, we've reached quantum mechanics and things like this. Now it's difficult again. But we made 350 years of progress that was incredible through experimental control, allowing us to filter our theories, and completely wrong things were thrown out, right? Even though very, very powerful people believed them, only because of controlled experiments. And that's how we made progress. If you look at chemistry, now I've put this on the x-axis. I've put these things arranged for how similar they are to human organizations. So physical systems are not that similar, right? Chemistry is a bit more similar to what we're interested in, which is organizations. If you go to biology, you're now a lot more similar to something that we actually deal with. So biological systems have to deal with the same problems that human organizations have to deal with, right? They have to deal with, I'm talking about, microbiology, bacteria, I'm talking about all these things. So they have to deal with uncertainty in the environment. They have to deal with how to grow in a reliable way. They have to deal with how to innovate, and they have to deal with risk. So all of these things are analogous, to the problems that we're actually interested in, which is how to manage organizations for the same thing: growth, risk, innovation, uncertainty. But we can do controlled experiments in biology. So this means that the theory that we've developed in biology is of much higher quality than the theory where we are not able to directly do controlled experiments. And so what I'm proposing to do with my consultancy is translate biological theory, which is obviously worked on by thousands and thousands of biologists over 50 years since the discovery of DNA, to understand how we tick and how we solve these problems. And obviously you don't get as good quality theory from translation, right? Because it's only an analog, but it's going to be way better, I think, than what we already have. And so that's what my organization is about. It's about translating biological research to help us to understand and measure our organizations. So how would we translate something like that, right? Well, you need a model of understanding, a theory that naturally goes across both. And it turns out that technology is the right people to do this, to pioneer this, because we're all familiar with computation. We're all familiar with what computers do. But the theory of computation is also how cutting-edge biologists are starting to understand biological systems. So I went to this workshop in 2018 at the Royal Society, and it was an international, interdisciplinary set of researchers who had all come together to study biological systems using computation as a model of how those systems work and how biological systems work. And obviously, that means that what we've learned about how natural systems compute in this broad sense, we can translate to organizations, because computer theory is just a model of work. It's just a model of complex work. Now we automate those things, but they can be random. They can be, what's the technical term is stochastic. So they can work with probabilities. All these things can be done in computer theory. And so we can use natural computation as a model of work. And so what do I mean by that? Okay, so here we go. This is it. This is how we translate this work. So let's start with a simple equation. A equals pi r squared, so the area of a circle. And the picture is of a black hole, actually, if anyone is aware. It's the accretion disk around the black hole. It's not quite a circle. You can see that. This is an actual image they've created of a real black hole. But anyway, if we calculate pi precisely and accurately, it goes on, obviously it goes on forever, it's an irrational number. But if we calculate it to a high precision, you get, let's say that, you get a long number. If we calculate it accurately but imprecisely, that's what that symbol is. It's not an equal sign, it's roughly equals 3.14. So now we've got accuracy that we've computed, but no precision. Now 3.14 approximately is not one number. What you're referring to is a range of numbers, right? So, the precision is telling you the range, right? It's telling you it's between 3.1, you've rounded it to 3.14. So to compute pi, what we normally do is start with something accurate and then get more and more precise. And actually, this is what we do in organizations, right? And we're very familiar with this sort of algorithm. But in nature, it turns out that the computation that's being done is often the other way around. We start off with something precise, and then we get progressively more accurate. So what do I mean by this? Well, if I look at binary classification, this is where we take, say you have a medical test and you want to test somebody for COVID. And what you're interested in is not one result, you're interested in a whole set of results, right? So we have a set of patients to test, and this diagram is showing you that on the left-hand side are all the people who have COVID, and in the green hemisphere, you've got all of the people that the test correctly says have COVID, right? And on the red side, you got, on the right-hand side in total, you've got all the people who don't have COVID, and the red disc is the people who this test incorrectly says do have COVID when actually they don't. So we're going to find the set of those with the disease, and we might start off with precision, right? So we start off, let's just say, with one person correctly identified as having COVID, and then we improve the precision, we still improve the accuracy now, and it's very precise. But if we want to improve the accuracy further, we're going to have to potentially lose some of the precision, right? So we're going to have to, it's easier to get a test that is accurate without being so precise. It's very hard to do both, right? But it turns out that accuracy is what nature is very interested in over precision, and it's interested in sets over the singular. So what do I mean by that? So, okay. So now we're looking at nature. So why do I say that nature is interested in the sets over the singular? The reason I'm saying that is, if you look at the tree of life, it's the number of ways to be alive that nature is exploring, right? Diverse ways to be alive. And obviously that's the tree of life on the right, an early version of it. But it turns out that population diversity is essential for natural selection to work, right? Because you need enough options for natural selection to promote somebody that is good enough. And so natural selection is operating within a set. And cutting edge biology by these people, Andreas Wagner, Alex Wissner-Gross, and AI research using biology to do AI research by Kenneth Stanley and Joel Lehman, this shows us that we can understand the fundamental thing that's going on here differently to the way we were taught. So instead of it just being survival of the fittest, which hopefully you guys remember from biology, and what Darwin used that later on in later editions, that's about optimization. So that's about precision over accuracy, right? The singular over the set. But we also have compute diverse viable options to survive and thrive. So this is about accuracy over precision. This is about computing sets over the singular. And this turns out to be important at lots of different levels, not just the tree of life, but within microorganisms. The robustness of an organism, such as ourselves, is by a lot of what we would call redundancy, which is a very loaded term. But what we're really doing is we're computing a large set of options, even within our bodies, to perform functions so that they happen reliably. So now we're getting to the kind of the crux of it. So in in an organization, we are familiar with this. So if you look at Google Maps, when you suggest, like I use Google Maps to get here, I'm sure lots of people are using this or a similar system. What we have here, typically with Google Maps, is it'll offer several options, right, as to a route within a certain precision, right? So the precision here is that within about 3 minutes of each other, these routes are giving you a set of options. Now, Google knows that it does not know all the requirements for your route. So it's giving you a set of options, and it's hoping that at least one of them is good enough for you. So if you, for some reason, don't want that route, right, maybe you don't want to go, it might be the fastest route, but it might be the less scenic route, or it might be that you're meeting a friend on the way and Google doesn't know that there's a waypoint that you're interested in, or it might be a certain transport that you don't like or whatever. But these 3 suggested routes mean that that Google is cooperating with you very effectively without knowing exactly what it is you want. And this is really important in organizations because we're constantly working in big organizations where we don't know exactly what's wanted, but we do want to work with people who are not giving us clear instructions or are in another team that don't have as much control. But we want to cooperate. And so this is what happens in nature. So why does nature want to compute as many paths as possible? Why is accuracy so much more important than precision? When you have more ways to do something, it's more likely to happen and to continue to happen. Obviously, that's happening in the tree of life. Lots of things are going extinct, but not everything. So we also have statistics telling us this. And this is a simulation of what's called a Galton board. And it's just showing you that these balls are falling down with a 50% chance of falling left and right each time they fall, right? But on average, there are more ways to end up somewhere in the middle than to the edge. Now, it's easy to block the bins at the bottom that are on the farthest side because there's only one path to get there. You can't get back. If you go left once, you can't get to the rightmost one anymore. So it's very easy to block those singular paths, but it's very hard to block the paths towards the middle unless you go right, obviously right to the end, the last step. So this is telling us something important about how to achieve success. So the set is more important than the singular. So nature knows that accuracy, and by the way, this ends up forming the normal distribution. That's what this approximates. So this is telling us that this is a way to provide a reliable service. And okay, the balls are falling and it's on average, this is what happens. But what if you're doing something once? Even if you're doing something once, it makes sense to have options, right? So cooperating to execute one task is also achieved by accuracy over precision. So if you're playing football and you have enough options, it's very difficult for the opposition to stop you passing the ball and retaining possession. And you pass to the person who also has options, right? So you're constantly conserving the options available, even though you only have one ball and you're only making one move at a time, right? So it's not about a portfolio. It's like Google Maps. It's having options so that when there are blockers, there are still options to continue. And so we make options for each other as a team. So it's a team game, basically, to offer options and to conserve options. And this is very different to how we think in organizations, where we're constantly trying to optimize. And so I'll explain what the difference is. Oh yeah, by the way, yeah, I mean, this is a deep principle. So we're only just learning this now, but it's 4 billion years of evolution has shown how this works. And it can be more important than survival of the fittest. It can actually override survival of the fittest. So this principle of cooperation is deeper than the prisoner's dilemma and deeper than game theory. And I say that because game theory is also important in evolution and biology, but it's not as prevalent as this method of cooperation. And it's deeper than modularity, which we're familiar with as engineers and is also present in biology, but is not as prevalent as this method of cooperation. So what's the most efficient way to make a paper airplane that flies, right? That's an interesting question that we're familiar with as, builders of things and working in organizations. What's the furthest flying plane design? Maybe we can get the team to design a paper plane that flies further by motivating them with an aggressive deadline, right? So that's precision over accuracy. right? So that's not a good idea. So I want to avoid OKRs with deadlines with unnecessary precision, right? Which is just efficiency worth a few cents on the dollar. What you want to do is choose OKRs that motivate higher task accuracy, which means that you promote teams that provide more options as to how to do something rather than simply try and find the best way to do it. So what's an example of this? Oh yeah, another question is this just about margin for error and contingency? I'll explain that it's not. But Google and Microsoft and American Airlines, they have collaborated to reduce global warming created by planes by flying from a selection of a choice of routes that are on average 2% less efficient, right? But by using a lot of data from satellites, they can choose flight options that reduce the formation of clouds caused by contrails, which is what contributes to global warming. So by reducing the deadline, the efficiency, the precision that we're going for, and offering options, there's ways to incorporate that result from that, even though you might not be familiar. And I'm not just saying, someone might say, well, the best way to do it is this way, so you've just created a new precise option, but it's not like that. In terms of margin for error, if you reduce precision of a deadline, that's fine. But unless you're also increasing the accuracy, which is computing, using that drop of precision to give you more options, right? You're not doing anything with that contingency. You're not providing options. You're just saying, I just want more space, which is dead space. But if you just have one way of doing it with less precision. So the Org2 manifesto, which stands for organic organization, is that we model tasks and that we have teams and OKRs that promote accuracy over precision. And so we compute tasks accurately, which means we compute multiple ways to do things, like how many ways are there to create this particular task, how many options do we have to do this? And we don't try and choose the best one or steer the manager to the best option. We try to conserve the options that are available because we don't know what other requirements are going to arrive later on. And that's going to change how successful we are as an organization. So we reduce the precision and we allow our managers to reduce the precision by which we sort of like deadlines in order to vary and create diversity in the options that we keep available to do things. And so blockers will appear and arrive late on, but we will find an existing route that we can move to that allows us to deliver all our requirements. So like in films you hear like this, the job is to hit the target, I don't care how you do it. And normally some incredibly violent thing happens after that. But other teams hopefully do care, you know, how you hit that target. And they offer you options to succeed rather than constraints about you have to do it this way. Because there's a way of cooperating, just like in football, to offer teams options rather than to give them constraints that they have to now fit, come what may. And so we value robust delivery over fragile transparency, because what's going to happen is that you're going to lose the ability to go into the detail of exactly how people are doing things, because they're keeping available options and they're moving from one option to another as they need to. So what that means is that you can't have the amount of transparency that people want. What that means is you have the flexibility to actually deliver as long as you've actually conserved those options. So the summary is accuracy over precision, and we value figuring out more ways to do things. So this is about us as human beings. We are what make technology robust. We're not the source of error, of human error. We're the source of flexibility that fixes things over and over again as they inevitably break. That's what makes technology work. It's a socio-technical system. So when I'm talking about computing, I'm talking about natural computation. I'm talking about us thinking of options, because we're the ones who normally have to do this. It's the technologists who are doing the computation. So as I say, it's because we believe that biology, it tells us this is what makes cooperation work. And I've got some example here of when you can model it explicitly. So this is a graph database modeling a tech strategy. And so this is an example of how you can make it explicit, because it's a mathematical concept that can be made programmatic. I'm not just talking about culture, I am talking about something real. And I can talk about this as a product that you can have to manage your tech strategy and model the different paths that are available, just like Google Maps, and that you want to conserve, basically. And yeah, so to return to the Great Smoky Dragon, Wheeler thought of a dragon as something that's big yet hard to see or measure. It could be something that nature knows how to compute, and we're still working it out, how to imitate it. And yeah, these are some of the books that I recommend if you're interested in learning more about this. And obviously that's my website, turingmeta.org. Have a look, there are lots of talks on there, business ready sort of articles. And also thanks to these academic researchers who I've worked with over the last few years to develop these ideas, particularly Andrea Fantuzzi at Imperial. And thank you very much for listening. I really appreciate you taking the time to listen to this talk. Thank you very much.